Hello class, so this week's lecture is based on minerals and rocks, and first I wanted to talk about the rock cycle. There are three types of rocks, which are sedimentary rock, metamorphic rock, and igneous rock. So first I want to talk about the igneous rocks. So igneous rocks are formed when magma cools and hardens, and depending if it's below the surface when magma cools and hardens, this is known as intrusive igneous rock, and when magma cools and hardens above the Earth's surface, this is known as extrusive igneous rock. So an example would be a volcano, and the volcano erupts and the magma flows onto the Earth's surface. The magma will quickly solidify, forming extrusive igneous rocks. So the rocks that you see on Earth's surface, it's known as outcrop, and these rocks experience different processes which are weathering and erosion. So meaning that the wind, the flowing water, plants, animals, and many more, they can break down the rocks into smaller pieces, forming pebbles, sand, silt. So it's just breaking down the rock to much smaller pieces. And then these rocks, they end up being transported by the rivers, and as they're getting transported, it just gets the rocks get smaller and smaller, where eventually they end up at the end of the river delta, and this is deposition. The sediments deposit themselves, and the sediments start to layer on top of each other, and as they start to layer on top of one another, this is known as compaction, and these sediments are pressing into one another, filling in the gaps with more debris. So when these sediments are fully compacted, when there's a chemical bond occurring between these sediments, this will allow it to form a sedimentary rock. So you can think of the chemical bond gluing these sediments together, forming a sedimentary rock. As you can see here, the sedimentary rock, due to heavy burial, it can travel down below Earth's surface, and the sedimentary rock can transform into a metamorphic rock, but it can only transform into a metamorphic rock when it's exposed to high heat and pressure. So the high heat and pressure will transform the sedimentary rock, and it will change its formation, and this is what is called a metamorphic rock. So metamorphic rock is basically changing pre-existing rock, whether it's sedimentary rock, igneous, or another metamorphic rock. It's just changing its formation. And again, the process starts again when metamorphic rock begins to melt, and then magma all the way back down to the metamorphic rock. So that's the rock cycle. I just wanted to give a little preview of the rocks, and I wanted to give examples too. So for igneous rocks, this is an intrusive igneous rock. This is diorite, and it's made up of two minerals, plagioclase and hornblende. And this was formed within a mountain belt. And this is an extrusive igneous rock. It's an obsidian. So as you can see, this rock was formed from the magma as it cooled and hardened on Earth's surface, and it has a different texture. It's shiny and black. And the next one is sedimentary rocks. This is an example of shale. So you can see the compaction and the layers of how the sediments layered on top of one another and then bonded, forming a sedimentary rock. And this is composed of clay and silt, which is finer than sand. And this is a metamorphic rock, and this is slate. So this was previously shale, as you can see here, but since it was exposed to higher heat and pressure, it transformed into a metamorphic rock known as slate. So rocks are composed of minerals, one or more minerals. So for your lab this week, you all will be identifying the types of minerals based on their physical properties. So as an intro to minerals, minerals differ by chemical composition, and this allows them to have different physical properties that allows the mineral to be identified. So the following criteria is needed to be a mineral. It needs to be a naturally occurring substance, not being made by humans, an inorganic substance, not composed of living organisms, an orderly internal structure, and fixed chemical composition. So this is the criteria needed, and fun fact, ice is considered a mineral because it checks all of these boxes. And also, rocks differ from each other based on the environmental setting in which they formed. As what we learned from the rock cycle, they form either below Earth's surface or above Earth's surface based on different processes. So moving forward, minerals can be identified by their physical characteristics, and the 5 properties observed in mineral identification are color, 2, streak, the 3rd one is luster, and the 4th one is hardness, and the 5th one is cleavage fracture. So usually hardness is popular to identify a mineral, and we'll learn that later. But for the first one, color, some minerals have similar color, example gold, whereas some minerals come in a variety of color, for example quartz. So the presence and intensity of certain elements will determine a specific mineral color. So for example, on the left side we have malachite, and on the right side azurite. And this has a very deep green, whereas azurite has a deep blue. And this is due to these minerals having the element copper. So the copper element is within their atomic structure, so this is what gives off that deep color. Also, this is the variety of color amongst quartz, so it can range from purple to blue, and they are nice crystals to collect as well. So for the second one, it's another way to identify a mineral is by streak. So streak is the color of a mineral's powder. So as you can see here, when you scratch a mineral against a plate, you can see the color of the powder. Streak is a more reliable property than color because streak does not vary. So in this photograph, this is the same mineral, and that's why they have similar color. They have a similar color powder, but the reason that they look different is because of their texture. So this one's more coarse and this one's more smooth, but this is the same mineral. The third way to identify a mineral is luster. So luster describes the reflection of light off a mineral's surface. Luster is broken into 2 families, metallic or non-metallic. So we're not looking at the color of the mineral, but we're looking at how does the reflection of light look on the mineral surface. So once you have your mineral, you can use this flow chart, and you can identify it whether it's metallic or non-metallic. In this case, with this mineral, from using the flow chart, we would say that it's metallic and it's a shiny metallic. But there are a lot of options for non-metallic, and we will go through how they look, each one. So for non-metallic glassy, it has the look of glass, and for non-metallic pearly, it has that iridescent look, and for a waxy type of luster, it has an oil-coated substance type of presence. And for The fourth one, earthy, non-metallic. This has the look of soil or clay when light reflects off the rocks. Off the mineral. Excuse me, this is a mineral. And so the fourth way to identify a mineral is by hardness. So you can use the Mohs scale of mineral hardness. And this is named after Frederick Mohs, and he's a mineralogist who invented a scale of hardness based on the ability of one mineral to scratch another. And the hardness of a mineral is mainly controlled by the strength of the bonding between the atoms and partly by the size of the atoms. So in our next slide, we're going to look at the Mohs hardness scale. So as we can see here, the scale number is from 1 to 10, 1 being the softest and 10 being the hardest. And in the Mohs hardness scale, there are 10 minerals. So in this case, talc has a hardness level of 1, so it's considered the softest. And since this scale is based on minerals being able to scratch the other, all the minerals above talc can scratch it. And let's look at gypsum. Gypsum has a hardness level of 2. So gypsum can scratch talc, but it cannot scratch calcite because calcite has a higher hardness level of 3. So from what we can see, diamond has the hardest, is the hardest. So on this side, this is talking about what types of objects can scratch these, or the hardness level that can be able to scratch the minerals. So for fingernail, the fingernail has a hardness level of 2.5, so the fingernail can scratch gypsum and talc. So if you ever have a mineral and you're outside and you can scratch it, you'll know that the mineral has a hardness level below 2.5. So that is a way to look at Mohs hardness scale, and if you're taking a geology lab class, you will be using a kit that you can practice with testing the hardness of minerals. Next is cleavage and fracture. So the way in which minerals break is determined by the arrangement of its atoms and the chemical bond between those atoms. So the best way to determine cleavage and fracture is by the shape and design in which minerals break. So for cleavage, the definition for cleavage is that it consistently breaks or cleaves along a parallel flat surface. So in this diagram, we have, this diagram is using an axe to represent cleavage in a simple way. So this is an example of one plane of cleavage. So you can see here the axe is slicing it in one direction, and it has a top and bottom. So this is only one way that the axe can slice. So it's a one plane of cleavage. And an example of that is this mica. So when you have the mica, when you break it apart, it comes out into sheets. So think of the axe slicing it one way, and it's a sheet, so it has a top and bottom, so that makes it a one plane of cleavage. And this is, for this image, this is a two plane of cleavage, so the axe can slice it in two directions, so this way and that way. So when it breaks, it can only break in those directions, which makes it a two-way cleavage. So this is an example of a three plane of cleavage. So this is a cube. So as you can see here, there are three directions to slice the cube using the axe. And then this is another three planes of cleavage, and this is four planes of cleavage. So fracture is different than cleavage because, as you can see here, it breaks at a parallel flat surface, whereas for a fracture, it breaks in a rough or irregular pattern. So this is an example of quartz. And so when you break quartz, it has an irregular pattern, compared to mica, where it's like a flat surface, where it breaks at a flat surface. So this is this week's lecture, and please let me know if you need help regarding the lab, and thank you for watching.